Good afternoon, everybody. I'm Jay Ressler with GZA. Going to introduce our speaker today, John Sewell from GZA's Wisconsin office. He'll be speaking on the Milwaukee theater move. John's been an associate principal with GZA. Has over 30 years of experience. He served a number of geotechnical service types, including buildings, highways and rail, utilities, communication facilities. He was also the lead geotech design for 3 of the Wisconsin DOT's largest projects in history. John is a registered PE in 14 states and is a diplomat geotechnical engineer from the Academy of Geoprofessionals. The Milwaukee Theater was built in the 1920s and it's on the National Register of Historic Places. The Milwaukee Symphony Orchestra purchased the theater, knowing that they would need to expand the stage area, to accommodate their orchestra. So they had to move one of the walls outwards about 35 feet. John will be discussing the options in the systems they considered and designed for movement of the wall. Welcome, John.
I appreciate it. Sorry, everybody, that I'm not on video. I had a technical difficulty here, but anyway, we'll proceed. I'm grateful for the invitation to speak, and here we go. Sorry about that. Jay had given you basically a prelude into me. There's some more detail on me. I'm actually now registered in 15 states, but one point I want to bring up about myself that is near the tail end of this slide. I'm a member of Engineers Without Borders, have been for 7 years, and I'm also a mentor for the Milwaukee School of Engineering student chapter of Engineers Without Borders. This is a plug, but if you have not done anything with UWB, you should consider it. It is a great organization, and it allows young engineers to get training that they wouldn't normally get. And it allows them to design things and build things. I've been to Guatemala 7 times in 8 years, working on bridges, schools, and other types of infrastructure. The Grand Theater site, it's located in downtown Milwaukee. Now, everybody in the audience here from Rhode Island area, you probably know nothing about Milwaukee, but Milwaukee is 90 miles north of Chicago. It's right on Lake Michigan, and the site of the project is about 700 feet west of the Milwaukee River, which on the screen is the north-south trending toward the top of the screen river. There's also an east-west river that is the Menominee River, south of the east-west freeway that you can see there. And then there's a southern river, it's the Kinnickinnic River, and all 3 of those rivers come together in downtown Milwaukee. The area is urban, and some of the structures have been in place since the mid-1800s, probably not unlike urban areas out east, maybe a little bit younger, but in general comparable. This is a picture of a theater in 1940, and the only reason I'm bringing this up is there's a lot of history in this theater. The quality of that photo isn't that great, but on the screen it talks about James Cagney and others in a movie called The Fighting Something. And then there's a lady actress by the name of Lupe Velez in the Mexican Spitfire movie, which was 1940. So that's how I know the timeline of that photograph. The geotechnical conditions at the Grand Theater site, there's roughly 7 to 14 feet of miscellaneous urban fill with old construction debris. And that fill came about because the city of Milwaukee, not much unlike the city of Chicago back in the 1800s, with water levels where they were, particularly here, they wanted to raise grades, so they brought in materials from wherever they could find it, and that ended up creating an urban fill there. Below that urban fill on this site is a soft organic silt and clay estuarine deposits. I'm giving you some geotechnical parameters there for that material. Void ratio in the range of 1 to 3, so it's compressible. A C sub C value of 0.2 to 1, and a C sub B value of about 20 to 500 square feet per year. These soft deposits extend approximately 50 feet or more on this site, and locally they can go down to depths of 70 or 80 feet. In deposits, we get into glacial till, and the glacial till can be a granular till deposit or a cohesive till deposit, and that goes down to about 170 feet, and then we get into dolomitic bedrock below the till. The one thing about Milwaukee that is a little bit unusual is that the bedrock can vary greatly in relatively short distances. The downtown area is in a floodplain, but if you go 5 blocks west of the Grand Theater site, you get into some upland areas, and bedrock there can be so shallow that it's exposed. So in a distance of several hundred feet, you could have 200 feet of delta in bedrock elevation. The swamp or the organic deposits that are in this area, pre-development, were used by Native Americans for a food source. They harvested wild rice, they caught fish, so it was an area that was settled for a long time with the Indians, even before Eastern Europeans came in. But it also, with those deposits, has some geotechnical issues. Historically, structures used timber piles for support until the 30s, and then they switched over to pipe and to H piles. Pipe piles are probably used more predominantly in this area than H piles, just because we do find H piles sometimes go wrong in granular deposits. The whole Milwaukee area used to have large forests, principally of pine, red pine, white pine, and also tamarack. Those materials, particularly the tamarack, was a little more resistant to decay, and I'll talk a little more about that here in a moment. Secondary consolidation of these organic deposits is also a concern, and buildings have had long-term settlement for that reason. To give you a few project details, Jay alluded to this at the introduction, but the theater was constructed in the late 20s on timber piles. GZA, as part of the work that we've done on this project, we probably had 6 main tasks. The first task we were brought in on was to develop recommendations to support building additions. There are 2 additions that were added on to the original theater structure as part of our work, and 10 3/4 inch closed-end pipe piles were used for those addition supports. Theater stage, as I already mentioned, was too small, so we had to take the east wall and move it 35 feet east. That doesn't sound too involved, but the site is built with a 0 lot line prior to the renovations, and we had to move the wall into the 2nd Street right-of-way. And you can imagine most municipalities don't want to give up right-of-way if they don't have to. So that in and of itself took time. There were also utility relocations that had to occur: gas main, water main, storm sewer, sanitary sewer, telecommunications, including fiber optic lines. But there was also a 70-year-old steam tunnel. The steam tunnel I'll talk a little more about here in a bit, but the tunnel best we can tell, was hand mined in the estuarine deposits back in the late 30s, early 40s. We believe it was done under compressed air, and the local utility company, We Energies, they're very protective of said utility because it provides a lot of steam heat to buildings in downtown Milwaukee. I'm showing you a picture here of a timber pile that was under the south wall of the theater addition. The area where this pile was located was previously a two-story structure that they demolished, but in the interest of saving dollars, they wanted to see if they could reuse existing foundations. So we were tasked with evaluating piles, running load tests on timber piles, and giving them recommendations to do so. They also had to provide some supplemental support, but we did look at it. What I wanted to get out of this picture is the fact that on the left and right of the timber pile, which is centered on the screen, and that pile is approximately 14 inches in diameter, you can see soil deposits, grade deposits off to the left and to the right. If you look closely, and hopefully it shows on your screen, the white dots that are there, I believe visible, those are shell fragments that are part of that estuarine deposit that I discussed a little while ago. The other point I wanted to bring up about this particular timber pile, these were hand-dug excavations. The laborers that made the excavations hit the timber pile with the shovel, and you can see the scraping off of the outer covering of that pile. This particular pile, we cut out the 18-inch section, put in a load test frame and tested it, but I retained that core, and that particular pile is a red pine, and it was in fair to good condition. I guess the interesting point I wanted to bring up about it, based on growth rings of that tree, the tree was 60 years old when it was cut. And with the age of the building, that tree started growing about 152 years ago. So that, just from a general perspective, is, I think, a very interesting aspect. We at GZA, we considered 3 different types of systems to support the wall move infrastructure. We looked at either driven piles or helical piers used only for wall move infrastructure support. We also looked at new structural slabs, and then subgrade improvement methods. And these 3 methods, as you can imagine, they all have advantages and disadvantages. The piles and helical piers, if they were done solely for the wall move, that would be a fair amount of additional cost. The upside was movement was dependable or defined. Same thing with new structural slabs in the basement of the building and the at-grade portion. If those were structurally supported, wall movement over this would not be a big deal, but there was cost and time. So we put most emphasis, after we discounted the first 2, into a subgrade improvement method. We developed this improvement method, and we took into account the fact that the building floor slab in the existing building had been so dissected from new improvements that it had to be removed. And the underlying soil, we felt we could build a system that could, once the floor was reconstructed, to support that cribbing to minimize movement. The time frame we were given for this wall movement was originally going to be 2 to 4 weeks. Then it got fine-tuned down to 2 to 4 days, and that was somewhat dependent on the soil and the movement infrastructure response to the loading. Settlement was measured during the move so that we could confirm acceptable movements, or stop things and re-shim if necessary, if movements were starting to be objectionable. The ground improvement system that we came up with, it's not unlike things like used on other projects we may have if we're in the geotechnical field, but we used geofabric in particular, Tensar 5X, GeoGrid, and Mirify HP 370 high strength geotextile. We layered that in between gravel, and this sketch on the screen shows what that system looked like. At the bottom of this slide, you can see the soft silt soil. We took a 4-inch thick layer of 3-inch maximum size aggregate and worked or physically had that pushed into the subgrade. We placed a 12-inch thick layer of Wisconsin DOT road gravel, which is basically an inch and a half maximum size, about 5 to 12% fines. Compacted that in place, placed the 5XT GeoGrid on top of that, added another 12-inch thick layer of compacted road gravel. Then we placed a 4-inch thick drainage layer and had a 6-inch floor slab constructed on top of that. The slab did have reinforcement. It was number 4 bars, but I do not recall the specific spacing of those bars. This improvement system for the project at hand, it strengthened the subgrade, but we ended up using 900 tons of gravel to accomplish that. The GeoGrid and the geotextile provided confinement such that the gravel layers with that confinement were relatively rigid and much, much stiffer than the underlying subgrade soil, so that the resulting stress into that soil was small, and correspondingly the resulting sediments were also small. The steam tunnel that I referred to earlier briefly presented an issue. The wall had to move over that steam tunnel under the new building framework, which was the old right-of-way. The structural engineer analyzed the tunnel and tried to determine what would be an acceptable stress level to impose into that 70-year-old tunnel, and the tunnel wall thickness based on historic drawings is nominally 10 to 12 inches thick with reinforcement. We looked at stress distribution with the GeoGrid gravel geotextile layer, and the load on that tunnel was about 5.2 psi, which from a structural perspective is not a great amount of increased load, but on a 70-year-old tunnel that has some aging to it, it was a concern for the utility. This particular sheet that I'm showing you is a plan view of the wall move infrastructure. In the center of the screen, you can see up and down blue lines and crosshatched black lines. Those are the framing system that went in underneath the wall, and the arrow points to the location of the wall prior to the move. The arrow to the lower right is the wall final location, and then the distance between the steam tunnel location, 2 arrows, is where the steam tunnel was located. And that tunnel is a north-south tunnel, which would be up toward the top and to the bottom of the plan on the screen. This particular cross-section is in an area where that steam tunnel is shown. The tunnel crown is at elevation 83. This is a site elevation, so it's not really tied into USGS or anything like that. And then the upper floor elevation there is at 93. This plan also shows wood cribbing, and that wood cribbing was set on wood mats below the cribbing and extended up to that blue beam, which is part of the wall move infrastructure. I've got a few photos here that show the details on the building wall itself. The view you're currently looking at is the east side of the east wall, and there's a supplemental steel frame that was put in to support the wall during the move. You can also see this wall is got brick facing. It's a double white wall, and at the top of the wall is terracotta finish. And at the lower portion of the screen, you can see some openings where it looks like elements have been removed. Those three areas were fake balconies. They were called balconettes, but they removed those because they were made out of terracotta, and they were concerned that the wall move, particularly in the differential movement, might cause cracking, and they wanted to save that material to put it on once the wall got to its final location. This wall move was a joint effort, actually a team effort, but International Chimney Corporation on Williamsville, New York, and expert house movers out of Sharpton, Maryland, moved the wall in 6 hours on August 13th. International Chimney and expert house movers were names I think don't really do them justice. They're very well thought out companies, and particularly expert house builders. That name is definitely a misnomer. These two firms jointly have moved some of the largest structures in the continental U.S. They've moved structures that range from lighthouses to big buildings to airport hangars, things of that nature. The arrow here is pointing to the wall framing system that was put in. That sign that says C.D. Smith. Below that, you can see brick that had been removed to allow the infrastructure to be placed. This is a close-up view of the northwest corner of the building. That beam in the left foreground is one of 6 beams that supports that east wall. To the right, you can see a brick wall behind that jack, and that's the north wall of the building. This wall weighed 1,200,000 pounds, and it was raised by 24 lift jacks, one of which you see here, moving in unison to maintain level and reduce potential cracking of the wall. I'm going to go into a brief discussion of soil consolidation. For those of you who are geotechnical engineers, this will probably bore you, but for those of you who are not, basically a saturated soil, when it's loaded by some load of any way, shape, or means, first thing that happens is pore water pressure increases in that deposit. As the water in the pores drains out, the pressure will reduce, and then the consolidation will take place at that point in time. But the rate of consolidation is dependent on the soil permeability, and less permeable soil takes longer to drain. This wall move was so fast that, in essence, the soil didn't really have time to react, and the pore water pressure definitely didn't have time to react, so that there was minimal dissipation of pore water pressure, and correspondingly the settlements were small due to small consolidation. This is a view of the northeast corner of the building. The east wall is to the right. There's a framing system in place. There's a vertical red line at the tip of that arrow. That's a cut line where they physically cut through the 2 life wall thickness from the top of the wall to the bottom, and that wall is 87 feet high, to separate it from the other structure to remain. This is a view of a roller beam jack underneath the yellow support frame. These horizontal jacks that were set on these roller beams were put in, and they had a 5-foot stroke. So in essence, they would clamp to the underlying light-colored beam you see, and all of these jacks on 6 of the roller beams would move in unison and move the wall in 5-foot increments. Once the wall got moved, it had to be attached to the new location. This is a photo of a welder attaching a stub column. The stub column is from the welder's hands down in that photograph. And he's putting a plate over the ends of the flanges, and then he did a full penetration weld through the entire beam that's shown. You can tell the old beam because it's got gray mortar stains in the upper portion of that photograph. This is a view of the wall at its final location after the move. You can see the framing system on the left and right of the wall, inside and outside. And the steel frame in the foreground, that's a portion of the building addition that's sitting on new given piles. This is the backside of that same wall. You can see those dark vertical columns. There's 6 of them across that are supporting the overall wall system. Details of this move, in case you're interested, and if you're not, I'm going to get into it anyway, but the planning and execution took 14 months. The cost of the wall move proper, just the movement, the infrastructure, bringing in international chimney, and expert house movers was $1.5 million. The building and the owner received a tax credit of $30 million from the federal government because, as Jay mentioned, this building is on the National Historic Register and they want to maintain structures to the extent they can. The speed of this wall move was an amazing 0.0011 miles per hour, which equates to about 5.83 feet per hour. The total settlement measured was 1/4 of an inch, and that was about 1/2 of the maximum movement that they desired. We calculated approximately 1/2 inch with our system, and we did not see that. I think that had to go along with the discussion I mentioned of the permeability of the soil, the quick movement, and the soil didn't have time to react. The wall movement infrastructure in and of itself had 8 inches of travel, but they wanted to, under the first blush of this project, keep movement to an inch, inch and a half. C.D. Smith, as I mentioned earlier, they are the general contractor for this project, and they had time-lapse photography that they took during the wall move. I'll show this video for you. This is roughly a 20-second video for a 6-hour time frame, and you'll see it's done in stages which correspond to those 5-foot jacking limits, and enjoy. Sorry about that. This is a picture of the theater and the stage after the wall move completion. I did not take this picture, but I borrowed it from the Milwaukee Symphony Orchestra. You can see the immense detail in this structure. Back in the 20s and 30s, they did very ornate decoration. The stage that you see, the back of the stage with the yellow paint, that stage is the back wall that was moved, and previously it was about half the depth that you see in that photograph. This is a picture I took when I was inside the theater from the stage looking to the northwest, and it shows additional detail and beautiful aesthetics. So with that, that is the presentation I have. I'd be happy to discuss any questions that you may have, but feel free. It looks like Andrea Morrison here. Jay, do you want me to read that?
Sure, would you like to read that?
Sure. Andrea Morrison asked, as someone who has never heard of this theater or project before, is that the only wall that could have been moved? Seems like a lot of work between the utility relocations and figuring out how safely to move a historic wall into the street with risks of collapse. Is this the easiest only option for expansion? It's a good question, Andrea. it was really the only wall that could be moved, and reason being is that the stage was, the theater could not be retrofitted with its ornate accompaniments to do anything except expand the stage. If they moved the stage westward, it would have created a reduced number of seats in this facility. It was not an option.
John, we have another question. Was it common to build structures out of terracotta during that period, during that time period?
Yeah, it was. Terracotta in this case was done for, say, surface aesthetics. As I mentioned, at the parapet and at these balconettes that were put back in after the fact. But yes, it was very common. City of Milwaukee City Hall, which was built in the 1880s, has much terracotta, and terracotta is problematic because it's so settlement sensitive, but it's very aesthetically pleasing, but it doesn't handle much movement.
Well, John, I think that's all the questions that we have posted. John,
Okay,
thank you very much for presenting today. Also, thank you to Chad Morrison, our Rhode Island ASCE president-elect, for producing it. As a thank you for presenting, we're going to make the Rhode Island ASCE is going to make a $100 donation to the Theater Restoration Fund.
that's great.
I have just a couple announcements. I wanted to let everybody know Professor Lee at URI is going to be offering a sustainable pavement design session this summer of 2021, the session one. Our next live stream is on May 20th at noon time, where Ralph Verastro is going to be talking about the FIU pedestrian bridge collapse. And we will also be installing the new Rhode Island ASCE officers at that meeting. Thank you, everybody, for attending today.